Thank you, Professor Kuhn, for such a nice introduction, and thank you everybody for being here today. Today I'm going to present my thesis about physical exercise as a preventive strategy for disorders affecting the brain, with a special focus on its effect on neuroinflammation. But before I start this, I want you please all to stand up and participate in a short exercise, because we will be physically inactive now for a while. Some of the research in my thesis is about Alzheimer's disease, and this is the most common form of dementia. Those of you who believe that physical activity can prevent or decrease the risk of developing Alzheimer's, those who believe this, please sit down now. Thank you, and now the rest of you may sit down. So we'll see after this presentation, some of you may have changed your beliefs regarding this. We will see. But I will start now by refreshing the knowledge about the very broad range of disorders included in my thesis work, ranging from brain ischemia and vascular dementia over to neurodegenerative diseases such as Alzheimer's and Parkinson's. It's a very broad range of disorders included. And brain ischemia can be viewed as an acute disorder, since the occlusion of the cerebral vessel will lead to immediate lack of oxygen and neuronal death in the brain. And this can cause life-threatening symptoms. And some of these features are shared by vascular dementia, because as Georg told you, there are also acute microinfarcts contributing to this disorder. But in addition, this disorder is also characterized by a more progressive development, because it doesn't lead to immediate life-threatening symptoms, these infarcts, but rather a progressive loss of neuronal function, which is also the case in Alzheimer's and Parkinson's, since they are neurodegenerative disorders. And as Georg told us, these disorders are also characterized by the contribution of accumulating and aggregating proteins. We have amyloid beta in Alzheimer's disease and alpha-synuclein in Parkinson's disease. And these are contributing to the pathology progression. Then these disorders also affect different regions of the brain. And for brain ischemia, of course, the region affected depends very much on the site of the occlusion. But one region that is specifically vulnerable to lack of oxygen is the hippocampus. And this is also a region that I focus on in my thesis work. It's a region involved in memory formation. And it's also the region affected in our mouse model of this brain ischemia. In vascular dementia, it's mainly the white matter that are affected, containing nerve fibers that are connecting different brain regions together. In Alzheimer's, it's cortex and also hippocampus that are affected early in the disease pathology. And this leads to memory disturbances. Whereas in Parkinson, it's mainly the substantia nigra that is affected, with death of dopaminergic neurons as a result. And then the pathologies in these different brain regions also leads to different broad range of symptoms in these patients. And many of these symptoms can also be measured by behavioral tests in animal models of these disorders to get an idea of the progression of the pathology in the brain. In brain ischemia, it's common to see cognitive dysfunctions, so problems with memory, and also difficulties to move parts of your body, so motor symptoms. Whereas for vascular dementia, one of the most common symptoms are the cognitive symptoms, so memory problems, and also for Alzheimer's, since these are dementias. Whereas Parkinson's disease, it's the movement dysfunction that is the most commonly seen. Then all of these very broad range of disorders also have another symptom in common, or there is a symptom that is present in many patients with these disorders, and also included in my thesis. And I'm talking about depression, which is not only a symptom, but also a diagnosis that is common in society, and it affects people, and not only people affected by these disorders, but also other people across all ages. And not so much is known what is actually causing depression, but one thing that is known is that many depressed patients have dysfunction of the HPA axis, which is an axis involved in regulation of stress response. And then these disorders also share another feature that contributes to the disease pathology. And I'm talking about the contribution of microglial neuroinflammation to disease pathology. In many patients with these disorders, there can be seen post-mortem in their brain tissue an increased level of neuroinflammation and also activated microglial cells. So what are then these microglial cells doing in the brain, and how can they contribute to disease pathology? So primary microglia is the primary immune cell of the brain, and in the resting brain, or in the healthy brain, they are in a resting state, looking like this. So they have long, branched, elongated processes with which they sense the environment for potential threats to protect the brain. And they also contribute to brain homeostasis by secretion of trophic factors to support the neurons in their functions. But in the diseased brain, or with an insult, microglia can retract its processes and round up like this. And then it becomes activated. And depending on the stimuli, microglia can become activated into two different functional profiles. The one is the classically activated M1 microglia, which is pro-inflammatory and potentially also toxic to neurons. And the alternative activation is into the so-called M2 profile, which has been suggested to be more anti-inflammatory and also to be neuroprotective. And once these microglial cells are activated, they will start to proliferate to increase the cell numbers. And they will also secrete effector molecules, such as cytokines, that are inflammatory signaling molecules that can affect the inflammatory status in the brain. And pro-inflammatory cytokines will increase the inflammation, whereas anti-inflammatory cytokines will reduce the inflammation. And this is, of course, a very simplified description of a complex reality. And it's also a description that is highly debated at this moment. But I still want to share it with you because it's the common view in this research field. So then the idea is that there is a balance between these two extreme states, and in the healthy brain, this balance is more or less maintained. But many studies indicate that in the diseased brain, this balance might be lost in favor for the more pro-inflammatory, potentially neurotoxic microglia. And this can contribute to disease progression. So what can then exercise do to help with this? Well, a lot of things happen when we exercise. First, there is an immediate increase in cortisol and adrenaline, which are stress hormones that are implicated in the brain and body stress system. And if you remember this HPA axis, I told you this was dysregulated among many depressed patients. So the idea here is that exercise may fine-tune this system back to a functional state again, which might be beneficial for example, in depression. In addition, exercise also includes muscle movements, and this will lead to the secretion of myokines, which are cytokine-like molecules. And in the context of exercise, they has been shown to reduce inflammation, which also may be beneficial. And other studies are showing that exercise may also favor the maintenance of microglia in a resting state so that it can maintain brain homeostasis by secreting trophic factors to support the neurons. And if you remember this imbalance in activated microglia seen in this thesis, what exercise may do is to reestablish this balance, and some papers even indicate that it may favor the so-called anti-inflammatory and neuroprotective phenotype. So this was the knowledge in the field when I started my thesis work, and now I will show my contribution to the field. And for those of you who had looked through the book, you may recognize this picture. It's an overview of all the 6 papers included in my thesis work. I also color-coded them since I used 2 different approaches in my work. So the pink ones are based on an experimental approach where I investigate the molecular effects of running interventions in mouse models of brain disorders. And the green ones are based on an epidemiological approach where I investigate how a physically active lifestyle is associated with or affect the risk of developing some of our most common brain disorders in humans. And my 6-year-old daughter, when she saw this, she thought it looked like a thread of pearls. So what I'm going to do here today is to guide you through this pearl by pearl, and I will start with the first one. So in paper 1, we investigate how microglia contributes to brain pathology in brain ischemia in a mouse model. And our hypothesis here was that microglia can worsen the pathology of the brain ischemia. And to test this hypothesis, we compared normal wild-type mice with mice lacking the galectin-3 protein, which is microglial protein. And then we subjected them to common carotid artery occlusion. So we occlude these big arteries going to the brain. And this will cause a global brain ischemia with specific damage in hippocampus, if you remember this region involved in memory. And after a few days of recovery, I will assess memory function with the Y maze and collect samples. And we could see that mice lacking this galectin-3 protein, they had less microglial response seen in IBA1 staining in hippocampus compared to wild type after ischemia. And they also had a higher number of surviving new M-positive neurons in the hippocampus compared to wild type mice after ischemia. And if we look at wild type mice, what brain ischemia does is to induce a significant memory dysfunction in the Y maze test. But our mice lacking galectin-3 did not develop significant memory deficits in this test. So with this data, we concluded that galectin-3 contributes to harmful microglial activation, at least in the context of brain ischemia in our mice. So then I wanted to start with my exercise intervention. That's what I'm here to do. So we wanted to know if running could help and reduce this pathology in this mouse model. And the hypothesis here was that running would be beneficial in this context. So to do this, we use only wild-type normal mice, and we occlude common carotid arteries, these big arteries. So we use the same model to induce brain ischemia. But before this, we subjected one of our groups to 4 weeks of treadmill running. And then after ischemia, we perform behavioral tests and collect samples. Unfortunately, our running mice had fewer surviving UM-positive cells in the hippocampus compared to the sedentary non-running mice. So in this case, it seemed rather detrimental to run. And we could also see that our running mice behaved as if they were stressed by the running. They were more anxious in the open field test, and they had elevated levels of corticosterone. And corticosterone is the most correlated to human cortisol, so it's a stress hormone. And the elevated levels of this stress hormone in our running mice also correlated with fewer amount of surviving positive cells in the hippocampus after ischemia. So the running did not really work the way we thought. And for the next coming studies, we wanted to assure to have a running that is not inducing stress. So in a subset of mice, we instead allowed them to run voluntarily in the home cage in running wheels. And this time, no anxiety was induced and the corticosterone levels were normal. So this is the intervention we will use for the next coming paper. And the conclusion of this one is that the forced running may induce a harmful stress response, at least in the context of brain ischemia. But before I performed my next running intervention study in mice, we had the opportunity to look and investigate how a physically active lifestyle affects the risk of developing some of our most common brain disorders. And in this paper, we focus on how it affects the risk of depression. And I think that some of you might already heard about the Vasaloppet studies, since they have been circulated in media recently. But for those of you who have not heard about them, I will just briefly describe the setup. We followed almost 200,000 Swedish participants in the Vasaloppet long distance ski race. And we compared them to an equal amount of sex and age matched controls from the general Swedish population. And then we followed them for up to 21 years after participation in the race to see how many of them develop, in this case, depression, by taking out the diagnosis set in the patient registry. And for both men and women that were skiing, being a skier was associated with a lower risk of developing depression, about 50% lower risk compared to the general population. But when we focus instead on the impact of physical performance level on the risk of depression, we could see differences between men and women. And to do this, we only focus on the skiers, and based on the time it takes for them to complete the race, the finishing time of Vasaloppet, we divide them into 3 groups. So one is the fast, medium, and slow skiers. And for men, being a fast skier was associated with a further lower risk of developing depression compared to a slower male skier. So this being fast seemed to add an additional benefit in this case. Whereas among women, the pattern was completely the opposite. We have the fast skiing woman here. And yes, it's very far from being statistically significant, but I still wanted to show that they are not similar, the patterns. And before leaving this, I also want to point out that even the fastest skiing group of women still had a lower risk of developing depression compared to the non-skiing women in the general population. So it was still beneficial to be a skier if you were a woman. And the main conclusion of this paper was that a physically active lifestyle is associated with a 50% lower risk of developing depression. And in paper number 4, we continue with this Vasaloppet cohort, but this time we investigate the risk of developing Parkinson's disease, the movement disorder. And we could see that skiers had about 30% lower risk of developing Parkinson's disease compared to the general population. At least when we look early in the follow-up, because after about 15 years of follow-up, the lower cumulative incidence of Parkinson among the skiers seemed to approach that of the general population. And that made us wonder whether physical activity really conveys protection against the Parkinson pathology in the brain, or if there is something else that can explain this pattern. So in this paper, we discussed the possibility of a motor reserve. And the idea here is that if you're physically active, you will develop a higher motor reserve. So let's see, we have two people here, one physically active, let's say a skier in our cohort, and one that is physically inactive or less active, the general population seen here in red in our cohort. So if you have a higher motor reserve to begin with, even if you have the onset of Parkinson pathology at the same time or at the same age, the person having a higher motor reserve, it will take longer for this pathology to actually cause the onset of Parkinson's symptoms, which is the requirement to have the clinical diagnosis. So then maybe this person will have a higher number of years without symptoms and potentially a better life quality, maybe. And we look again on our data. And now we'll focus on those that we followed for the longest time. So these are participants recruited in the 90s. And again, we can see this pattern that the lower levels among the skiers approaches that of the general population with some time. And this is what would be predicted by this motor reserve hypothesis. It's also known from other studies that the incidence of Parkinson plateaus at an earlier age among women. And if we look specifically only on women, we could see a complete overlap in the cumulative incidence of Parkinson between the skiers and the general population towards the end of the study. And this is also in line with what this motor reserve hypothesis would predict. So with this data, we speculate that physically active individuals may develop a higher motor reserve, allowing them to sustain more Parkinson pathology before the onset of Parkinson's symptoms. In paper 5, I look instead on the risk of developing dementia in this Vasaloppet cohort. And what is new in our study compared to previous study in the field is that we distinguish between the two most common forms of dementia. Alzheimer's disease, which I told you about in the beginning, where you stand up and sit down and exercise. And this is the most common, affecting 2/3 of all dementia cases. And then we also include vascular dementia, which is the second most common. And we believe it's very important to distinguish between the two of them because they are caused by very different underlying pathologies, and physical activity might not affect them equally. I should also say that this paper is a combination of epidemiological data from the Vasaloppet cohort together with experimental data from a 6-month-long voluntary wheel running intervention in our Alzheimer's mouse model, 5xFAB. And this mouse model recapitulates many features seen in Alzheimer's patients, such as the accumulation of this amyloid beta protein, the development of behavioral deficits, for example, memory problems, and also the very early contribution of neuroinflammation and microglial activation to disease progression. So that's the reason we choose this mouse model. But I will start to share with you the skiers data, where we could see that our Vasaloppet skiers had about 40% lower risk of developing vascular dementia, the second most common form of dementia, compared to the general population. But for Alzheimer's disease, the most common form of dementia, we could not detect any differences between skiers and the general population. And this is in line with our experimental data, where as long as 6 months of wheel running in our Alzheimer's mice did not reduce the levels of these A-beta proteins in hippocampus. In addition, synaptic proteins are needed in order for two neurons to communicate with each other, for example, in hippocampus for forming new memories. And again, running in our intervention could not improve this, the levels of two synaptic proteins that we measured in the hippocampus. So our conclusion in this study is that a physically active lifestyle is associated with a lower risk of developing vascular dementia, but not Alzheimer's disease. But I was not fully satisfied with this because, as I told you, this animal model that we use, this 5x FAD model, also have a contribution of neuroinflammation to progression of the pathology. And it has been shown in numerous studies that exercise can reduce inflammation in the brain of experimental animals. So I wanted to try in a paper number 6 to see if it could at least reduce the neuroinflammation or other behavioral deficits in this mouse model, even if it does not affect the amyloid beta pathology. And again, we use the same set of mice as in paper 5. So we allow them to run for 6 months. But now I perform other behavioral tests, and we investigate other stainings. And regarding neuroinflammation, we could not see any differences between the running mice and the sedentary control mice when it comes to the total number of microglia, IBA1 positive cells in the hippocampus. And when we focus specifically on activated microglia or pro-inflammatory activated microglia that are positive for galectin-3 in the hippocampus, we could not see any differences between sedentary and running. So no effects on this marker, at least. When it comes to behavior, this model is known to develop hindlimb clasping, which is thought to reflect the A-beta pathology of the spinal cord in these mice. And our running mice developed this pathology earlier than the sedentary. And in addition, another feature that is developed in this mouse model is abnormal exploratory behavior in the elevated plasmase. And this has been suggested to reflect the disinhibitory tendencies seen in Alzheimer's patients. And again, our running mice had more pronounced abnormal behavior in this test. So the conclusion in this paper is that voluntary running does not ameliorate neuroinflammation or behavioral deficits in 5x FAD model, at least not with the markers and behavioral tests we used. And now I have delivered conclusions to all the 6 specific aims of my thesis, and it's time to tie it all together and to deliver some more general conclusions to the 2 general aims I had, one experimental and one epidemiological, but I will start with the experimental, focusing on the neuroinflammation and behavior in animal models, where my data suggests that running does not reduce the molecular or behavioral hallmarks of Alzheimer's in the 5x FAD model, at least not with our markers and tests. And running do not affect the total amount of microglia in the hippocampus in the context of brain ischemia or Alzheimer's, at least not in our models. And maybe most importantly, forced running may induce a harmful stress response, and this may interfere with the beneficial effects of exercise. And this is maybe the most important experimental conclusion of my whole thesis, because this really stressed the importance of considering stress when designing experimental running interventions in the future. And regarding epidemiological conclusions, my data suggests that the physically active lifestyle is associated with a lower risk of developing depression. And when it comes to the impact of physical performance level on the risk of depression, being a fast skier, this impacts risk of depression differently in men and women in our studies. Furthermore, physically active lifestyle is associated with a lower risk of developing Parkinson's disease. And here we speculate that physically active individuals may develop a motor reserve, allowing them to sustain more Parkinson pathology before the onset of Parkinson's symptoms. And last, a physically active lifestyle is associated with a lower risk of developing vascular dementia. But for those of you who might believe in the beginning of this presentation that physical activity may be associated to a lower risk of Alzheimer's, I have to make you disappointed because I could not confirm such an association in my thesis work. But I think that's a good example of the fact that we should not regard exercise as a universal miraculous treatment strategy to prevent all disorders affecting the brain. And I also know that many other studies reveal positive effects of a physically active lifestyle on life quality and also on maintaining cognition, even in patients with Alzheimer's. So there are still many good reasons for all of us to keep up the physically active lifestyle. And with these words, I just want to thank you all for coming here today, and especially thanks to Georg for taking your time with my thesis, and to my supervisors, Thomas Steyerboy and Jan Lexell, as well as to my wonderful colleagues and collaborators during this process. So, thank you very much.